Good morning. Today we're going to talk about Math 111, Section 2.2, graphing linear equations, or I call it graphing lines, and also kind of cover Section 2.3, slope of a line. Alright, I'm going to assume that we all know about the Cartesian coordinate system, in other words, the XY plane, and basically your solution sets here will be two-dimensional, so we can graph things now in two dimensions. The y-axis will be referred to as the vertical axis, and the x-axis will be the horizontal axis. The Cartesian coordinate system, the XY plane, is divided up into four quadrants, labeled in this fashion: quadrant 1, quadrant 2, quadrant 3, and quadrant 4. And from the top right quadrant, we go in counterclockwise order, of course. In the first quadrant, please notice all x values are positive and all y values are also positive. In the second quadrant, of course, in terms of the x-axis, we're left of 0. 0, 0 is the origin, by the way, of course. In this quadrant, all x values are negative and y values are positive because the y values are above the x-axis. In the third quadrant, of course, if you're left of 0, your x-coordinates will be negative, and if you're below the x-axis, your y values will also be negative. So both coordinates are negative in the third quadrant. Of course, in the fourth quadrant, x is positive and y is negative. Alright, so we're going to assume that everyone is familiar with the XY plane here from your first course in algebra, and that you know how to plot points. Alright, so we're going to go on then to plotting lines or graphing linear equations. If I give you an equation like this and ask you to graph it, y equals minus 1/2 x plus 3, well, what we usually do is make a table of values, establish through a trial and error process a set of three ordered pair coordinates that will solve this equation simultaneously. Alright, let's see. We can find, notice we've got a multiplier of minus 1/2 here times x. So if I pick my x coordinates with a little finesse, I won't have to deal with unpleasant fractions. We try to steer away from fractional coordinates as much as we can. Sometimes we have to deal with them, but I don't think we will have to here. For example, if I pick x values that are multiples of 2, this fractional coefficient will cancel out, and I'll have whole numbers to deal with in terms of these coordinates. For example, 0 is a multiple of 2. 0 is a multiple of anything. If x is 0, well, this equation tells me y equals 3. Similarly, if x equals positive 2, right? Positive 2 times minus 1/2 is negative 1, and negative 1 plus 3 is 2. And if x is negative 2, well, negative 2 times minus 1/2 is going to be positive 2, and 2 plus 3 is 5. Huh? Oh, let me check that. We've made a mistake here. Let me erase this. Let me show the work on this. If x is minus 2, let's show that substitution. Alright, if I make that substitution, x equals minus 2. Minus 2 times minus 1/2 is positive 1, right? And then 1 plus 3 is 4, so not 5. Please make that correction. When x is minus 2, y is positive 4. Alright, so I can graph these in the xy plane. I'll do the best I can sketching this freehand. If x is minus 2, y is 4. Let's be up here. If x is 0, y is 3. And if x is 2, y is 2. Alright, it takes 2 points to determine a line, but we usually look for three coordinates to graph lines of this type, so we have what we call a third confirming point. If you make a mistake in the other two, in either plotting of either of the other 2 points, that will be revealed by a third point. So I can then connect these dots, and I label the axes, and I label the line with the equation that generates it. And there is the graph of y equals minus 1/2 x plus 3. Note, every point on this line satisfies the equation y equals minus 1/2 x plus 3. Every point on the line, or I should say every coordinate of every point on the line, solves the equation y equals minus 1/2 x plus 3. Okay? Alright, so I know we've done this before, so let's run right to another example. How about graph y equals 1/3 x plus 1. Alright, y is already solved for us, so basically I can pick x values that are convenient and establish 3 points, 3 pairs of coordinates that solve this equation, and hence I can then graph the solution set. If x is 0, what's y going to be? Well, clearly 1/3 times 0 is 0, and y is 1. Alright, there's a special name for this point. This is called the y-intercept. If when x is 0 here, you know that the point indicated is then the y-intercept. You're going to be intersecting the y-axis at some point. If x is minus 3, well, minus 3 times 1/3 is going to be minus 1, and minus 1 plus 1 is then 0. All right, this point is called the x-intercept. If y is 0, then this indicated point is the x-intercept. It's where you're going to hit the x-axis, where the line is going to intersect the x-axis. It's a minus 3 there. And let's get a third confirming point. If x is 3, well, 3 times 1/3 is 1, and 1 plus 1 is 2. Alright, so with these 3 points, I think I can sketch out a fairly good graph. Again, bear with me here. I'm trying to do this freehand. Yes, you will have to buy some graph paper for the course. I think a package of graph paper at the bookstore, 50 sheets or so, is about $2, and that'll get you through this course easily. Alright, so let me plot these points. When x is minus 3, y is 0, meaning you're on the x-axis, hence the name x-intercept. If when x is 0, then y is 1, hence the name y-intercept. If x is 3, 2, 3, y is then 2. And it looks like these points are collinear. Right? If x is 3, y is 2, and I'll then connect these dots, and again label the axes, label the line with the equation that generates it. Okay? Alright, let's try another one here. Graph. Now, the first 2 examples we did today, we had y was solved for. In other words, the equations were given to you in the form y equals something, and not all lines are given to you in that form. This is what they call standard form of a line equation. In other words, ax plus by equals c. A multiple of x plus a multiple of y equals some constant. Alright, so again, I'm going to try to use a little finesse so I won't have to deal with cumbersome fractional coordinate values, which are always tough to graph. If x is 0, what's y going to be here? Oh, I'm sorry. Let's see. 2x minus 5y equals 10. All right, please make that correction. 2x minus 5y equals 10. All right, if x is 0, clearly y is going to be minus 2. Minus 2 times minus 5 equals positive 10. So that'll give me one good place to start. If x is 5, I think we can see, well, 5 times 2 is going to be 10, and y will then be 0 to solve this equation. And if x is minus 5, y will be minus 4. I can check that out. 2 times minus 5 minus 5 times minus 4, is that equal to 10? And it is. I'll get a negative 10 plus 20 equals 10, so that checks. All right, so that gives me 3 collinear points. Wait a minute, I slipped here. All right. So using this table of values, I'm going to graph this line. Give me a minute here. I'm going to put the graph right here. The best I can. Not doing too bad today. When x is 0, y is minus 2. When x is 5, 2, 3, 4, 5, y is 0. So I've got the y-intercept and the x-intercept respectively. Please notice this point here on the table I'm going to label as the y-intercept. When x is 0, the indicated coordinate is then the y-intercept. Similarly, if y is 0, you're on the x-axis somewhere. Intercept. So this point indicated is the x-intercept. And minus 5 minus 4, 1, 2, 3, 4, 5, 1, 2, 3, 4, puts me down here. And I'll claim that these points are collinear. So I connect the dots. Label the axes, and of course, label the line with the equation that generates it. Okay. Let's try another one. Graph. Let's see. X plus 2y equals minus 2. Again, I'll make a table of values. And I usually, should be a y. I usually try for the intercepts first. So, sometimes we don't. Depends on if you end up with fractional coordinates or not. I think we're okay here. If x is 0, if I sub x equals 0 into that equation, I'll get the y value of minus 1. If y equals 0, clearly x is going to be minus 2. So I've got, this is the y-intercept. If x is 0, this point is then the y-intercept. And if y is 0, this point is then the x-intercept. And I'll need a third confirming point. And I think we can see if x is 2 and y is minus 2, that will indeed solve this equation. Let me check it. 2 plus 2 times minus 2, is that equal to minus 2? I believe it is. 2 plus minus 4 is minus 2. Alright, so I've got a set of 3 points, which is plenty to graph a line equation. If x is 0, y is minus 1. If x is minus 2, y is 0, and if x is 2, y is minus 2. And so all these points look like they're all on the same line, so I'll connect the dots. Yeah, hang on. Try it again. Alright, so I label the axes and, of course, label the line with the equation that generates it. Okay? Let's try another one. Graph 3x equals 4y minus 11. Alright, this one's out of the homework list, and the book asks us to graph this using intercepts. Using the x and y intercepts. Well, this looks innocent enough, but the trouble is these intercepts are going to involve fractional coordinates. Now, we try to stay away from fractional coordinates when we can, but sometimes we're just stuck and we've got to, especially when we're instructed specifically to use them. Alright, if x is 0 here, what's y going to be? Well, I'll substitute. 3 times 0 equals 4y minus 11. Well, 3 times 0 is 0. And so if I add 11 to both sides, I get 4y equals 11. And if I divide both sides by 4, y equals 11 fourths. Well, we were instructed to use the intercepts, so even though the intercepts has a fractional coordinate here, we're going to have to do our best in graphing it. 11 fourths. Alright, similarly, if y is 0, let me substitute y equals 0 and solve for x now. I'll get the x-intercept. So 3x equals 4 times 0 minus 11. So 3x equals minus 11. So x equals minus 11 thirds. Alright. So I'll put those two pairs of coordinates on my table of values, and these are what I'm asked to use. Let's see, I'll do my best to graph these. Now I can only be so precise here, doing things by hand without graph paper. If x is 0, y is 11 fourths. Well, 11 fourths is just short of 3, right? 12 fourths is 3, so I'll put 11 fourths right there, just short of 3 on the y-axis. Now, minus 11 thirds, if x is 0, if y is 0, x is minus 11 thirds. Well, minus 12 thirds is going to be minus 4, so I'm going to be just short of minus 4 on the x-axis. Alright, so I claim that's good enough here, according to the instructions of our problem in the text. We are told to use the intercepts. Alright, I've done my best to graph the fractional coordinates of those intercepts, and I will label the line, of course, with the equation that generates it. Okay? Alright, I want to talk about another type of line here. Let me get a new screen. How about if I ask you to graph something like this? X equals minus 4. Well, the first thing you'll notice is y doesn't even appear in this equation. So if I try to make a table of values, and essentially what we're saying is y can be any value, and x is always going to be a constant negative 4. Right? So if I graph the set of points that solve this equation, it's going to be all the points in the xy plane that have an x coordinate of minus 4. In other words, y can be anything, but x is always going to be a constant, negative 4. I think you'll agree with me. This is going to be a vertical line, and nothing really sacred about the value minus 4 here. Any graph of the line of the form x equals a constant is a vertical line. So let me write that down. If x equals a constant, then you've got a vertical line. Your x coordinate never changes. Okay? Similarly, let me graph something of the form y equals 2. Well, again, if I notice that x doesn't even appear in this equation, so x can range between any value, and y is always going to be a positive 2, positive 2, positive 2. This is really the set of all points in the xy plane that have a y coordinate of positive 2. And if I graph this set of points, I'm going to get a horizontal line with a y-intercept of positive 2. Let me clean this up. There we go. Right, so y equals 2 is going to be a horizontal line. The y-coordinate never changes, so I get a horizontal line. And again, nothing sacred about y equals 2 here. I could have played this game with any value. If I graph any line of the form y equals a constant, I will always get a horizontal line. Y equals constant, horizontal line, x equals constant, vertical line. Alright. Alright, now that we've talked about graphing lines, I want to move on to the next section, section 2.3. is entitled Slope of a line. Now, what does the slope do? Well, what it does, it gives a numerical measure. Slope is really a numerical measure of what I call the steepness of a line. As you know, the slope, the letter we use to indicate slope is M. M is from the French for monter. It's a verb with the er ending, indicates a verb with the it's really the French word for to climb. All right, your slope, as I'm sure you know, is defined as the ratio of rise to run between any 2 points on the line. What do I mean by rise? Well, some books indicate it as delta y over delta x, meaning change in y over change in x. And a little more algebraic definition would be this, more formal definition. If you've got 2 points, x1, y1, and x2, comma, y2, 2 different points with 2 different coordinates, my change in y will be simply the difference in the y coordinates over the corresponding difference in the x coordinates. Alright, so I usually define what I call my slope triangle. My rise is going to be the vertical distance between those 2 points, and the run is going to be the horizontal distance between those 2 points. Alright, so informally we like to think of slope as rise over run. And let's jump right to an example here. If I ask us to find the slope of the line through these 2 points, minus 2 comma 4 and 3 comma minus 4, what I usually do is interpret the first point mentioned as x1, y2, and the other one x1, y1, and the second one is x2, y2. The labels really don't matter. You can take these points in any order you like, as long as you keep the y's with the corresponding x's in order. So my slope is going to be, well, y2 minus y1 over x2 minus x1. It's going to be minus 4 over 3 minus 2. Be careful of the signs here, and note subtraction is not commutative, so you end up with a minus 8 over positive 5. Alright, so that means my ratio of rise to run in this line is minus 8 to 5. If I graph these points, take a minute to graph them, see if I can squeeze them in here. Minus 2 comma 4 is up here somewhere, and 3 minus 4 is down here somewhere. If I connect those points, indicating a line through those 2 points, I can then see the horizontal distance between those 2 points is a positive 5, and the vertical distance, if I count the squares, is going to be negative 8. Alright, so let's see, my run here is 5, and notice my line falls from left to right, so my rise is really a negative 8. I've got a negative rise if my line falls left to right. Okay? Alright, if your slope is negative, as it is in this case, I have what is called a decreasing line. Alright, meaning decreasing left to right. Okay, going down left to right. Let's try another one. Let's try one with a positive slope this time. Find slope of line through minus 1, 3 and 2, comma 6. You can take these points in any order you like. You can label either one x1, y1. You can label either one x2, y2, as long as you keep the order consistent in the slope computations. The other one keep x1 with y1 and keep x2 with y2. My slope is going to be y2 minus y1 over x2 minus x1. What does that turn into? Well, in the numerator I get a 3, in the denominator I also get a 3. Well, 3 over 3 turns into 1. Well, that means my ratio of rise to run is really equivalent to 1 over 1. Alright, if I plot these 2 points, let me see if I can get them all on the same screen here. If x is minus 1, y is 3. If x is 2, y is 6. Hang on a minute, I put the point in the wrong place here. Hang on a minute. Alright. If x is minus 1, y is 3. Supposed to be right here. Please make that correction. If x is 2, y is 6. 1, 2, 3, 4, 5, 6. And if I draw that line between those 2 points, I can see that the horizontal distance between those 2 points is positive 3. The vertical distance between those 2 points is also positive 3. So my ratio of rise to run is 3 over 3, which indicates a 1. Alright, so here the slope is 1. And notice this line increases left to right. Let me write that down. If your slope is positive, as it is in this case, that means you've got an increasing line. When I say increasing line, I mean increasing left to right. Okay? That's the usual convention. Alright, so there's a couple of examples of slope calculations of what it means to have a positive or a negative slope. Let's talk about some special cases here. Slopes of horizontal and vertical lines. Those are special things that are going to happen here in these two cases. Let's take a horizontal line. Y, remember from last section, y equals a constant is a horizontal line. Alright, if I graph this line, one, two, three, four, five, I get a horizontal line with a y-intercept of positive 5. And I'll label this line y equals 5. Alright, if I ask you, what is the slope of this line? Well, your slope is always your rise over run. But in a horizontal line, there is no rise. Right? The line never goes up, never goes down in terms of the y coordinate. So my rise in a horizontal line is 0. And 0 over anything, it doesn't matter how much I run left to right, 0 over anything is always 0. So hence I can conclude that the slope of a horizontal line is always 0. So let me write that down. Horizontal line always have slope equal to 0. Horizontal lines, slope is 0. Okay, so it really doesn't matter the 5. Nothing sacred about the 5 here. I could have played this game with any line of the form y equals constant. So no rise means a slope of 0. How about vertical lines? Now, let's take an example. Well, x equals constant is a vertical line, right? So I'll take as an example here, x equals 3. Nothing sacred about 3 here. If I graph this line, let me graph this quickly. X equals 1, 2, 3. Well, this is going to be a vertical line with an x-intercept of 3. Y can be anything, and x is always 3, 3, 3. Do my best to sketch out a vertical line here. If I was to ask you what the slope of this vertical line is, well, slope is always rise over run. Now, this is somewhat similar to the horizontal case, except instead of there being no rise here, there's no run here. Right? The vertical line is all rise. So no matter what rise I take into consideration here, the run will always be 0, and division by 0 is undefined. So in this case, with a vertical line, since my slope calculation will always turn out to have a division by 0, we say a vertical line has no defined slope. Now please don't confuse that with zero slope. Zero slope is the horizontal case. no defined slope is the vertical case. All right? Let me stress that. I think I've got some room down here in a different color. I'll say horizontal lines always have a slope of 0, and vertical lines will always have an undefined slope, or our book calls it no defined slope. Division by 0 is undefined, hence vertical lines will have no defined slope. Okay? Alright. One more subtopic I want to talk about before we call it a day is parallel and perpendicular lines. Let me get a fresh screen here. Parallel and perpendicular lines. There's something special about the slopes between parallel and perpendicular lines. That's what we're going to investigate the rest of today. Let's talk about parallel lines first. Well, what does it mean for two lines to be parallel? Parallel lines, the formal definition is they never intersect. Well, I think you'll agree with me if I sketch out some parallel lines here, and if I indicate a slope triangle under these lines indicating the ratio of rise to run, I think you'll agree with me that if lines are parallel, they have to have the same slope. If they did not have the same slope, then sooner or later one line would overtake the other and intersect. All right, so the idea here is parallel lines have equal slopes. Okay? We can make that a little more formal. If line 1 is parallel to line 2, then the slope of line 1 equals the slope of line 2. And of course the subscripts here are referring to lines 1 and 2 respectively. Okay? Alright, I think everybody can believe that without too much argument. Perpendicular lines, it's not quite as intuitive. Let me write this down. Perpendicular lines. What does it mean for two lines to be perpendiculars? Well, they intersect, as you know, at a 90-degree angle. Now, the slopes of these lines could be all over the place. Well, if I was to graph a set of perpendicular lines, it doesn't quite look perpendicular. Let me try it again. Let's see, I've got one line here. Let's say I've got a line with a pretty steep negative slope. If I just draw another line here, yeah, it looks a little better. I'm trying to indicate a 90-degree angle here. These are perpendicular lines. Okay? Perpendicular lines, I'm sure you've heard this before, have negative reciprocal slopes. And most students don't have too much trouble with the parallel case, but with the perpendicular case, sometimes this gets mixed up, so please remember this. In other words, well, let me give you an example. If line 1 has a slope of minus 3, okay, and I ask what is the slope of line 2, assuming they are perpendicular lines, what would the slope of line 2 be? Alright, if L1 has a slope of minus 3 and if, let me give it to you in algebraic terms, if L1 is perpendicular to L2, then what's the slope of line 2? And it's going to be the negative reciprocal of minus 3. Well, what's the negative reciprocal of minus 3? Well, the negative of minus 3 is 3, and the reciprocal then would be 1/3. So if line 1 has slope of minus 3, line 2 is going to have the negative reciprocal slope. Alright, the book has a bunch of standard questions regarding parallel and perpendicular lines, and this is a Regents type question I'm sure you've probably seen before. Let's see, this is exercise 42 in your homework list on page 157, and they pose this question: is the line through 6, 4 and 8, 5 parallel? Oops, hang on a minute. Is the line through 6, 4 and 8, 5 parallel, perpendicular, or neither to a line with slope equals minus 2? Alright, kind of a standard question. I call these parallel, perpendicular, or neither type questions. Well, the first thing I have to do is compute the slope of this line through these 2 points and compare that slope to this slope. Alright, so the slope of the line through the given points is going to be y2 minus y1 over x2 minus x1. That's going to be 1/2, right? So I need to compare a slope of 1/2 to a slope of minus 2. And of course, you'll agree with me that these are negative reciprocal slopes. Negative and reciprocal. So slopes are negative and reciprocal. And when slopes are negative reciprocals, that means perpendicular lines. Okay? So the answer to this question would be perpendicular. Let's try another one from this homework list. This is number 52. And let's see, we are asked to compare line through minus 5, 4 and 5, 4. And we're also asked to consider a line through 2 other points, minus 6, minus 2, and 3, minus 2. And we are asked the question, are these lines parallel, perpendicular, or neither? Well, of course, I need to compare the slopes. What's the slope of this line? Well, again, if I claim this is x1, y1, and this is x2, y2, I'll take y2 minus y1 over x2 minus x1. Alright, so the slope of this line, well, 4 minus 4 is 0 over 10, and of course this turns into a slope of 0. So this line here has a slope equal to 0. Notice, could I have spotted that? Notice these y coordinates are constant. And if y equals constant, you've got a horizontal line. And all horizontal lines have a slope of 0. So you may not have needed to compute the slope from first principles if you spotted those y coordinates are the same. And notice we've got a similar situation in this second set of coordinates. Y is constant across those 2 points. And if y is constant, that means you've got a horizontal line. And if you've got a horizontal line, the slope is 0. Alright, if you didn't spot that, you could have ground out the slope from first principles. Slope is y2 minus y1 over x2 minus x1. My slope is going to be, well, guess what? The numerator turned into a 0 over 9, and again the slope here is 0. Alright, so the first line has a slope of 0. The second line has a slope of 0. So if I ask you, are they parallel, perpendicular, or neither? Of course we'll say parallel as my final answer. Alright. Parallel lines have equal slopes, and slopes with equal lines, equal slopes are parallel. Alright, we're approaching the 47-minute point. We'll call it a day. We covered sections 2.2 and 2.3 today, and the homework assignment will reflect that. And please remember your online exam for both sections 2.2 and 2.3 will be included in this online class folder. That's all for today.